Hello everyone, welcome to the Mechanism channel. Today, our topic is PFMEA, which stands for Process Failure Mode and Effects Analysis. PFMEA, or Process Failure Mode and Effects Analysis, is a structured approach used to identify and mitigate potential failure modes within a manufacturing or assembly process. Its purpose is to evaluate process steps, determine what could go wrong, and implement corrective actions before defects occur, improving product quality and reliability. Whereas DFMEA, or Design Failure Mode and Effects Analysis, focuses on the product design itself, PFMEA addresses risks that arise during the production or manufacturing processes. It is widely used in industries like automotive, aerospace, electronics, and medical devices, where process stability is critical. Key components of PFMEA. First, process steps. These are the specific actions taken during production, such as machining, assembling, or painting. Next, potential failure modes. These are the ways in which a process could fail to meet its intended function, like poor fit or wrong material usage. Then, potential effects of failure. This is the impact of failure on product performance, safety, or quality. For example, component failure or system malfunction. Severity, or S, is a rating of how serious the effect of the failure would be, typically on a scale from 1, which is low, to 10, which is high. Occurrence, or O, is the likelihood of the failure occurring during the process, rated from 1, unlikely, to 10, frequent. Detection, or D, is the ability to detect the failure before it causes a defect, rated on a scale of 1, very likely to detect, to 10, unlikely to detect. Finally, risk priority number, or RPN, is calculated by multiplying severity by occurrence by detection. Higher RPN values indicate higher risks and guide prioritization for action. Importance of PFMEA. First, it prevents process-related defects. PFMEA allows you to proactively identify potential defects in manufacturing processes before they occur, reducing costly defects, rework, and scrap. Next, it enhances process efficiency. By analyzing potential failure modes and their causes, PFMEA helps identify opportunities to streamline processes, optimize workflows, and reduce cycle times. Then, it improves product quality. Mitigating potential failures in the production process helps ensure products meet their quality specifications, improving customer satisfaction, and reducing returns or warranty claims. It also supports compliance. Many industries, especially automotive under ISO TS 16949, require the use of PFMEA as part of their quality management systems. Lastly, risk management. PFMEA enables teams to assess risks and prioritize actions based on the likelihood and impact of failures, helping focus resources on the most critical areas. PFMEA process. Step 1. Define the process. Identify the key steps in the manufacturing or assembly process. For example, the process of assembling a car engine or producing a plastic part might be broken down into stages like material handling, machining, assembly, and inspection. Step 2. Identify potential failure modes. List all possible ways each process step could fail. For example, in a welding process, A failure mode could be insufficient weld penetration. Step 3. Identify the effects of failure. Analyze the potential effects of each failure mode. If the weld fails, the result might be structural weakness, which could compromise the safety of the final product. Step 4. Assign severity, occurrence, and detection ratings. For each failure mode, rate the severity of its effect, the likelihood of it occurring, and the likelihood of detecting the failure before it reaches the customer. This helps quantify the risk. Step 5. Calculate the RPN. Multiply the values for severity, occurrence, and detection to prioritize which failure modes require the most attention. Step 6. Develop action plans. Focus on failure modes with high RPNs and create action plans to reduce severity, occurrence, or improve detection. This may involve process redesign, additional quality checks, or improved training. Step 7. Implement corrective actions and monitor. After actions are taken, reassess the RPN values to confirm that risks have been reduced. Continuous monitoring ensures that new failure modes do not arise over time. Let's look at a simplified example in an automotive assembly line, where a critical process involves attaching car doors to the body of the vehicle. Step 1. Process step. Attaching car doors to the car body using bolts. Step 2. Potential failure mode. Improper bolt tightening. Bolts are either too loose or too tight. Step 3. Effect of failure. Loose bolts could lead to doors rattling or falling off, causing a safety hazard. Over-tightened bolts could damage the bolt threads, leading to door misalignment or difficulty in opening and closing the doors. Step 4. Severity, occurrence, detection ratings. For loose bolts, severity is 9, occurrence is 4, and detection is 5, resulting in an RPN of 180. For over-tightened bolts, severity is 6, occurrence is 6, and detection is 3, resulting in an RPN of 108. Step 5. Action plan for high-risk failure modes. For loose bolts with an RPN of 180, the action is to implement torque sensors in the tools to ensure proper tightening and automate error checks during assembly. Also, add real-time alerts for operators if torque values fall outside the acceptable range. For over-tightened bolts with an RPN of 108, the action is to improve tool calibration procedures and train operators on correct bolt tightening methods. Introduce additional inspection steps to check for over-tightening. Step 6. Implement corrective actions. After the introduction of torque sensors, real-time alerts, and improved training, reassess the process. The new RPN for loose bolts reduces to 90. The new RPN for over-tightened bolts reduces to 54. This shows a significant reduction in risk. The risk priority number, or RPN, is essential in PFMEA because it helps prioritize risks. By focusing on the highest RPN values, organizations can allocate resources to address the most critical issues first. In the example above, the team prioritized addressing loose bolts with an RPN of 180 over tightened bolts, which had an RPN of 108 due to the higher safety risk. Let's talk about the benefits of using PFMEA. First, proactive defect prevention. PFMEA identifies potential issues in manufacturing processes before they cause defects, reducing the likelihood of rework, recalls, or safety incidents. Second, improved process control. PFMEA allows teams to build in safeguards, error-proofing techniques, and control plans to reduce variability and ensure process stability. Third, cost savings. By preventing process failures, companies can save on warranty claims, rework, scrap, and production downtime. And finally, compliance and certification. Many industries require the use of PFMEA to meet quality and safety standards, such as ISO 9001, IATF 16949 for automotive, or AS 9100 for aerospace. PFMEA is an essential tool for improving manufacturing processes by identifying and mitigating potential failures. It helps ensure higher product quality, greater process efficiency, and compliance with industry standards. By focusing on critical risks through RPN analysis, organizations can proactively prevent defects, leading to cost savings and improved customer satisfaction. Thanks for watching. Please like, share, and subscribe. Happy learning!